welcome back. So we will start from where we left. Okay. So what we have been discussing till now was the conformationally mobile macrocyclic systems and the routine way of rigidifying the macrocycle, which was via hydrogen bonding interactions. Now we will have to go to the aspect where the conformational rigidity is inbuilt into a molecule via controlling the sterics as well as torsional strains. How you leverage them or how you fine tune them in order to achieve a rigid macrocycle. Okay. So as we said previously also, there are literature reports. They have used these two hydroxy groups, bridge them via a methylene, and hence you can arrest this flipping. If you don't have the hydroxy groups, this structure would appear like a simple metacyclophane, correct? The metacyclophane structure is given here for your correlation. So if hydroxy groups are not present here, you will end up in getting metacyclophane, and yeah, you will end up in getting metacyclophane, and these metacyclophanes are conformationally flexible structures. Okay. So the intramolecular hydrogen bonding here will keep it as a crown. Right. Another way is to connect them through methylene linkers to make them crown. Okay. Whereas this is a non-covalent approach, whereas that is a covalent approach. So you can do this in order to achieve crown. So what we thought was, we wanted to use these alkyl substituents that you are placing here, because you would have used various aldehydes for condensation, and those alkyl chains could be modified appropriately to bring in sufficient steric strain around that region. Okay. So what we did was, we tried to vary various alkyl groups. Okay, and the first one is methyl, and then you have ethyl, and then propyl, and then this is isobutyl, and that is isopropyl, and then cyclohexyl. Right? Some of them already pointed out, sir, why not use cyclic system and all, right? So one could see, if you are varying these alkyl chains and use these corresponding aldehydes for the condensation reaction that you are establishing here, all these alkyl chains would be placed in place of R, correct? So that those are the locations where these alkyl groups would be seated. And finally, you repeat the same reaction that you did before to get this coumarinarine macrocycle. Okay. I want your attention on the yields that these alkyl chains have given when forming the macrocycle. Okay. Pay attention to the yields. So moment you move from methyl to ethyl, the yields have gone up. Ethyl to propyl, again it has increased, and propyl to isobutyl, again there is an increment, but moment you come to isopropyl or cyclohexyl, the yields have dropped again. Okay. To this series, we even tried using tertiary butyl. In that case, no yields. We couldn't get this macrocycle at all. Instead, it produced the linear oligomers or the polymers generated out of this condensation reaction. Okay. So this, through analyzing the yields, you can come to you get some information, which is that the branching, right? When you shift the branching from beta to alpha carbon, then the yields are lowering, and if you introduce more of the substituents or more branching at the alpha carbon, at the max you can have 3, like what you have in the case of tertiary butyl, completely, there is no ring formation, but it just opens up to form a linear polymerization. So what it means is, steric influence is very, very sensitive at that particular carbon, at the alpha carbon, which will not favor, right, the macrocycle if it is sterically very encumbered. For the ring closing to happen, there must be some freedom for these N's to come together to form the macrocycle, right. So, that was the hint we had. So, linear chains are okay to form the macrocycle, but if you impose some steric interactions or built in more steric interactions, what happens is they would probably rigidify, but beyond a point they don't have appropriate angle to form the macrocycle, so they would remain open. In that case, more of a polymer is generated. Okay, so this was the idea that we could get from here, and we studied afterwards all these compounds, whatever we synthesized by NMR spectroscopy. So, the NMR spectroscopy, if you do it at room temperature, as we said in the very beginning, for the alkyl chains that are linear, okay, the derivatives that had linear alkyl chains, you had a conformational interconversion from boat form of C2 to another boat form of C2, which we discussed in the morning. But moment you have a branching at the alpha carbon, which is isopropyl, when you have isopropyl here, right, what you saw was, even if you vary the temperature, the peaks do not split. We had it in the previous case where the peaks were splitting. When you go down to minus 90 degrees or minus 80 degrees, these peaks would split into two, indicating that there are two C2 isomers which are actually rapidly conformationally interconverting at room temperature. So, in this case, fortunately, we are not able to see any splitting of the peaks even if you lower the temperature to minus 90 degrees. It means you have conformationally locked the crown isomer to produce only crown, only one isomer. Okay. So, in the previous case we discussed that you start from boat, to generate another boat it has to pass through a high energy crown. Now, by putting in steric interactions, right, what you have established is the high energy crown, right. So, that is the conclusion. So, if you are, we also checked this, change this isopropyl to cyclohexyl derivative. If you do the same NMR spectrum, variable temperature, even for the cyclohexyl derivative, there is no conformational interconversion and there are no C2 isomers seen. There is always the C4 isomer only was seen in the solution, and that also did not split, those signals also did not split when you lowered the temperature to minus 90. Okay. So, this evidences that there is no conformational switching and there is only one conform.
Just a quick question.
Yeah.
This is a symmetric, so there is no optical isomerism, right, at any point?
No, in this case there is no optical isomerism. Yeah.
Supposing you tweak one OME to something else.
It will exhibit.
It becomes optically isomeric.
Yes.
Does it lock into a specific stereo configuration when you prepare?
Does it lock into a stereo configuration?
Either R or S, which one? Does it have a...
No, it will always result in a mixture of these two.
But have you tried that?
No. We had this.
Be a mixture. Because if it is that lower temperature, you can isolate the stereo configuration.
We don't induce, we don't induct it.
You don't do any asymmetric.
We don't induct the stereo. Correct.
Okay.
Otherwise, there is a possibility to.
That's a known case. I mean,
yeah.
You do it purposefully. But without doing it, even in a symmetric case, do you ever see, for example, in this, macrocycles are very different from the normal molecules for these kind of stereo.
Yes.
Do they lock into any specific stereo configuration?
Stereo
configuration?
No. In the previous case, sir, if I can go back. Correct.
And the carbon it becomes an optically optically active form.
There is no symmetry.
Then the synthesis, does it give you R plus S or only R or only S? He says it's R plus S. That's a question.
It is always a R plus S. Here also what we get, you can look at this particular starting material we have. This can have R, it can also have S. On the intermediate layer, in the structure, if you see from the top, the arrangement of the groups either are in the clockwise or they are in anti-clockwise direction. So this is a racemic compound.
This is a racemic compound.
This is a racemic compound.
It's not an optical.
It's not an optically pure compound. So you take this, further you do the synthesis to get this macrocycle. Again, the cyclic orientation, cyclic arrangement of this fluorophoric units also brings in and it also results in a racemic mixture.
Oh, I see. Because it's auto rotates.
Yeah, it auto rotates. So now the boy is trying to resolve it so that we get enantiopior isomers of these materials.
So these are what? D4H or C4V?
C4, it cannot be V, but it is a C4.
Oh, it's just a C4.
It's just a C4.
Because it's not a planar model.
Yeah, it doesn't have a plane.
Check.
What is the 2 RAC and 5 RAC? Is the racemic mixture?
No, 2 is a number just to indicate the compound, RAC is a racemate. And here also is a 5 is a number for the compound and it is again a racemic mixture. Yeah.
If you substitute beta substitute differently rather than methyl, the yields may change.
Beta substitution, the beta branching you are saying, instead of methyl, what is the group that you have in mind?
Phenyl or carbonate.
It will impose steric constraints again. It will bring in steric component inside. Because here you have only one carbon. Where is this? So you have CH, right? You are saying phenyl in place of methyl would bring in C and additional H, right? So this hydrogen could get inside.
I'm saying in the place of methyl itself.
Instead of this methyl, correct? Instead of methyl, you visualize a ring. Correct? These hydrogens would go in, but they are little away, right? But if you have 2 of the phenyls, probably it would bring in some kind of a steric. But I cannot guarantee whether it would behave the same way as your isopropyl is behaving. Okay? So, yeah. So in the case of cyclohexyl also, you will have, in the case of cyclohexyl also, you will have a similar scenario. So if you lower down the temperature, these signals do not split and they again confirm that these macrocycles behave rigidly. Okay? So simple conformational thing, analysis that we learnt, we can imply here to understand how these systems would behave. We also crystallized this compound. And as you are noticing from here, these 2 arms are facing upwards, not flat as you had seen previously. They are upwards and the opposite 2 arms are also pointing upwards. Okay. So this is a typical crown type of a conformation that is trapped by the substitution of isopropyl groups, right, at the R positions. When you convert this, when this isopropyl group is placed onto the coumarinarines R, right, in the methylene bridges, you again see a perfect crown for coumarinarine also. So what it means is in this macrocycle you do not have hydrogen bonding, but by changing the R to a sterically bulky group, you can achieve crown conformation. In this case also you do not have an intramolecular hydrogen bonding in the case of coumarinarine. So in principle they should flip-flop, right, converting from one boat to another boat. By putting isopropyl groups, they are locked up into crown. Both the solid state structure, the crystal structure and the low temperature NMR confirms that this molecule, both in solution and in solid, they have the same conformation. Okay, that is achieved. Now you may want to understand why this particular group and how this particular group has given it a crown conformation.
Sir, if I used to substitute the substituents in the coumarin ring, how it affect in the range of this in the crowns? So if I substitute in the crown, starting middle fluoro the coumarin ring இருக்கு.
Yeah.
அதுல வந்து நான் சப்ஸ்டிடியூஷன் கொடுத்தேன்னா இதுல வந்துட்டு என்னோட
See, if you are putting something on these edges, it is away from this particular backbone. That is not going to influence your crown shape, right? Because the crown is being built by the condensation with the alkyl, right? And coumarin, if you have any substitution here at this side, it is not expected to alter the crown geometry. Only when the steric crowd is built in at the alkyl region, then you are able to make this macrocycle rigid, right? And anything you do it on the periphery, that's not going to affect actually the geometry, okay? Now, this is the solid state structure, okay? What you are seeing here is simple hydroxy, methoxy, basic, the parent macrocycle. This is converted to this, you can see a perfect crown geometry here. The angle between these two phenyl rings, if you take, it is 79.97. If you just convert this hydroxy to methoxy, let us say octamethoxy resorcinarines, no hydrogen bonding, so it should be flexible, but if you put isopropyl groups here, they get rigidified, forming a crown. In the third case where you had coumarinarine, again there was no intramolecular hydrogen bonding to hold it as a crown. Now if you put bulky isopropyl groups, they form a nice crown. The angle between these two coumarinarines, right, is about 89.35, so close to 90 degrees. If you look at these two coumarins, so if you make a plane of this, you measure it, they are close to 90 degrees. So which is measured accurately as 89.35, okay. So this is rigid. This we know both in solid state also, in solid state also it is rigid. Now the cavity, because of the rigidity, it is confined, right. Because it is rigid, you can measure the dimensions as was shown that it was 13.5 angstrom or so from rim to the rim. If you measure, the dimension is about 13.5. So the cavity of that much big size. You can put in a big buckyball into the cavity. It is possible. Okay, so that much space you have. You can do any kind of molecular recognition. So this is to just to tell you how this steric influences are modifying. We are lucky enough to get some crystal structures for series of molecules. As you are seeing here from ethyl, you can see these two opposite rings are kind of flat, right, lifting up, and the opposite, the other 1 and 3 arenes are parallel, okay. Next, if you move from ethyl to isobutyl, where the branching was at the beta carbon, right, it is quite flat, right, very planar opposite rings, and the other two rings are just parallel. If you go further to cyclohexyl, these two arms are trying to come down, and because these two arms are coming down, the ones that are parallel would also open a bit to give not a perfect crown, but they are crown, okay, close to the crown. When you are going to isopropyl, it is very perfect. This is just the parent molecules. What you are seeing is the octamethoxy coumarinarines, sorry, octamethoxy resorcinarines. In this case, it is the coumarinarine. You can see from isobutyl to cyclohexyl to isopropyl, slowly it is conformationally locking to the crown, okay. So a simple understanding of your conformational analysis can help you to design macrocycles the way you want, right. And let's try to understand how these interactions are helping. We try to understand in a typical organic chemistry point of view. when you have, oh, I'm not supposed to. So, when you have simple methylene, let's say R is equal to methyl, right? The orange spheres that you are seeing are the methyl carbons. So, that methyl has 3 hydrogens, and the hydrogen that is there at the bridge is the methine CH, right? That connects the 2 phenyl part or coumarin part. And now if you look at this particular carbon, this is one conformation where all the CH3 hydrogens are staggered, correct? The way that we have drawn is all the CH3 hydrogens are staggered. This is the lowest energy conformation for this macrocycle because all the methyls are, hydrogens are staggered to the methine hydrogen, right? So, this conformation is both. This particular molecule, if you crystallize or do the low temperature NMR studies, you find that they have both to both interconversion. That we have studied also, we synthesized, we checked. Now, we increase one more methyl, which means in the methyl hydrogens, you remove one of the hydrogens and you add one methyl, then the methyl will become ethyl, correct? So, when you have ethyl, you have 2 scenarios coming into picture, right? Either the hydrogens can be staggered. When you put a methyl, then you would induce methyl can be staggered, right? And very importantly, don't forget these are all arene rings. So, the arene and the methyl will have Gaussian interactions coming into picture, okay? When do you say there is Gaussian interaction? When do you say there is only staggered? CH, CH, right? When they are like this, right? This is a staggered. What is the other form of it? Where the CH and CH are in the same plane, right? So, this CH could be tilted to 60 degrees, rotated. At that point of time, you will see the CH and CH lying in the same plane. That is called eclipsed conformation. Eclipsed conformation, if you arrange all the methyls, you expect that this conformer is going to be of higher energy when compared to that of the hydrogens being at the staggered positions, correct? That depends on the, why should this hydrogen, methyl hydrogen would prefer to go to staggered instead of being in eclipsed. Why? Would you say that steric or would you say that some other terminology? That's why I want to take a break and ask a question now. Hydrogens, CH, CH, lying in plane, the adjacent carbons hydrogens, right? Say here there is a methyl, methyl, and this is a methyl, this is a methyl, pretty typical ethane, right? Ethane's hydrogens, you can have only 2 conformers, eclipsed and staggered. Why should it go to staggered? Why not it stay at the methyl? At the eclipsed, sorry. What is the difference between torsional and steric? Someone said steric, now I am hearing torsional. What is the difference? Your answer is right. But what is the difference? When do you say it is torsional? When do you say it is Gaussian or steric? When there is a 4 atom connectivity, 3 bond in between, right? So, in this case you can say that H, C, C and the front H, CH. There are 4 atoms, but there are 3 bonds, right? And the interaction between the hydrogens, you call that as torsional strain. Torsional strain talks about the bond pair repulsions. The CH has a bond, this CH also has a bond, right? This bond and that bond, when they align, there is a repulsive interaction between them, right? That is a torsional strain and it does not lie. That is why eclipsed form is of a higher energy and it quickly goes to the low energy staggered form. So it wants to stay away from the repulsion. That is the torsional strain. When does the steric strain come into picture? Hmm?
Size of the atom.
Can you define the way I had defined? Torsional strain connects 4 atoms with 3 bonds. In that scenario, you have torsional strain. When does the steric strain come into picture?
And the radii between two of them is very less, their steric strain comes into play.
Radii between 2 of what is that about? Radii of what?
These two
Which 2?
constituents.
Substituents, not very clear. You are using the terminologies, but I am failing to understand. Steric effects, when do they come? Let's say we are not having 3 bonds. We have 4 bonds. That means there is a 5 atom connectivity. There is a H, right? CC, CC, CH. Propane, for example. That time you will start seeing the steric interaction. This is a simple difference that you must know, right? If it is 2 methyls, butane scenario, then you would start to see certainly sterics. You call that as gauche, correct? So in this case you had only torsional strain when R was methyl. When R became ethyl, you start to introduce one gauche interaction already, correct? That means you are increasing the energy of the conformer, particular conformer. So in this case, how many gauche interactions are there already? We could see that 1, 2, 3, 4 such gauche interactions are possible in this molecule. When methyls are coming this way, you get a gauche interaction. So in principle, you can have 4 of such gauche interactions. And what we saw was, when you have isopropyl groups, the number of gauche interactions have reached maximum. So instead of 4 there, you could see 8 of them coming into picture. That means every methyl will face an arene at some point, right? What is the other possibility? Methyl can go inside and have a gauche interaction with both of the rings. One methyl can have gauche interaction with both of the rings. But the internal space is not sufficient enough, like what you are having here. The inside space is not sufficient enough to keep all the 4 methyls inside. That is a steric problems, right? And because of that, you keep these methyls always outside the cavity, and the methyl now does not allow the phenyl rings to come down because the methyls are supporting from the bottom. So the phenyl ring always stays like this. This is the reason we understood, okay? In the case of tertiabutyl, if you move from isopropyl to tertiabutyl, always you have to have one methyl inside the ring. You force it to place it in the ring. You can have 1, you can maybe have 2, but when 3 of such units are formed during the synthesis, bringing the 4th one could be problematic. And that is why the ring closing did not happen when you wanted to synthesize tertiabutyl substituted compound. You didn't get the product at all, okay? Because the inside space is not sufficient enough to accommodate all the 4 methyls to put together. Maybe 3 formed, but the 4th one, if it has to come in, there is steric crowd. So it just goes away and forms a linear polymer or a oligomer, okay? That is the conclusive part. So whenever you have aromatic units, be it phenyl or coumarin, the arrangement of the methyls surrounding that methane carbon is going to be helpful for us to decide whether a macrocycle is going to be rigid or a macrocycle is going to be flexible. So, simply by applying whatever we learnt, we could make a rigid coumarinine. You can also estimate the steric strain energy or a ring strain energy because of the bulky substituents that you have put on the periphery. You will see from methyl to ethyl, it is increasing, from ethyl to isopropyl, it is almost double, and from isopropyl to tertiary-butyl, it is almost 4 times higher. So, you can also see the steric strain increases. Because of the steric strain increase, there is also ring strain formation increases, and because you have the maximum ring strain possible for tertiary-butyl, obviously the ring did not form, and hence it just opened up to form the microcycle. This particular calculation study with respect to conformation analysis was done by KMSR student. Okay, put in a lot of time to understand all these energy barriers, which conformers is low energy, which conformer is low energy, which is higher energy, how this conformational switching is happening. So, you can do theoretical calculations, you can make various conformers without synthesizing in the you can make them in the computer, energy minimize them, and then understand each of these conformers have how much energy and which is the lowest energy conformer, which is the highest energy conformer. Okay. So, close to 144 structures were evaluated, all their energies were calculated, and finally we could understand that these are the low energy conformers which are responsible for locking it into a crown conformation. Okay. So, it is a lot of study, and this was published in this particular journal. Now, we have the microcycle, we want to put into some application. We want to show whether our all the hard work has yielded some fruitful effect, right. So, in that perspective, we wanted to capture fullerene because, as I mentioned, the diameter of the cavity was 13.5. Fullerene as such, if you look at the rim to rim, carbon to carbon measurement, if you do, it is typically less than 10 angstrom. Having a 13.5 void, certainly it should be able to hold fullerene. Okay, this was our idea. So, we thought to titrate it. You take your macrocycle and titrate it with fullerene. Okay. We initially took a rigid macrocycle only and we titrated it fullerene. We added 300 equivalents of fullerene. Okay. If the interaction between the fullerene and your macrocycle is quite friendly, you just need 2 equivalents or 1 equivalents, immediately they would complex and form the donor acceptor kind of a complex. But here it did not happen. We went up to 300 equivalents to check, but complexation was not happening. What you are seeing in the UV visible absorption spectrum is just an increment of addition of fullerene. So, the bands are just growing without any change in feature. Okay. So, that indicates that there is no complexation. So, we have to come to a different approach. We plotted it different wavelength and there is no saturation. You keep on adding, absorption increases. So, we know that there is no complexation. Fine. We also monitored it with the emission. We also recorded the fluorescence because our macrocycle is already fluorescent. Okay, it has a blue emission, and blue emission means you should expect the emission peak around 430 nanometers. If you check here, the maximum is coming close to 450, right? So, slightly less than 450, so I would say 440 or so, that is the maximum that it emits. So, it is a blue emission, blue emissive compound, to which if you add fullerene, you are seeing the emission intensity decreasing, which means what? Fullerene suppresses the fluorescence intensity of your macrocycle. That means what? It binds, but it binds transiently. Your macrocycles are there. Fullerene is also there in the solution because you are titrating, right? Both of them are there. And in solution, they are dynamic. They come and hit each other and then they go. They come and hit each other and go. Moment they hit each other, you see the fullerene is coming down. Which means what? The interaction between the fullerene and the macrocycle is dynamic in nature. The more you add, you promote more interactions, and because of that, at any given time, if there is a meeting of fullerene and macrocycle, there is a quenching of fluorescence intensity. The net result is what you see as a diminishing of fluorescence. 1000 molecule and given time interacting with fluorescence gives you diminishing of energy. So the interaction between the fullerene and the macrocycle is a dynamic. But what we wanted was to form just a stable complex 1:1. We don't want this dynamic interaction to happen, right? So that was the objective, but we were not successful in trying the solution state experiments. My student was also telling, sir, we can check this dynamism versus static complexation via NMR spectroscopy. NMR spectroscopy also tells you if it is dynamic, in room temperature it should not show, right? So you don't see any shift at all in the signals. So that's what we also saw. When you varied the equivalence from 0.2 equivalence to 1 equivalent, we could do the titration and we see there is no signal shift. That also indicates that the interaction is quite weak or maybe very dynamic. They don't interact very strongly. So no complexation in solution at room temperature. Either by UV or fluorescence or by NMR, there is no complexation. Okay. Now there is another question, right? It is dynamic, but if you increase the interaction between these two, not by adding more amount of fullerene, but let us say you provide some thermal energy to it, so that these molecules which were moving slowly, now they would move faster, collide. Instead of 10 times, they would collide 1000 times, 1,00,000 times. And in one point, if they find the right orientation, they can be captured, right? So we call that as an entropy driven fullerene binding, because you are increasing the entropy by heating, right? So we took a solution of fullerene. Solution as such looks here, purple. Fullerenes, if you try to dissolve it in toluene, this is the color you get. Purple color solution, very beautiful. And put the macrocycle also, reflects it for 24 hours, immediately the purple color changes to somewhat brown orangish color, okay. And you can also see a nice precipitate at the bottom, which is quite surprising for us. So we weren't sure whether that is precipitate or your macrocycle is decomposed or what is happening there, we were not sure, right. So we isolated this somehow and we try to dissolve it in toluene or dichloromethane, for example. If it is only fullerene, it has a very poor solubility in dichloromethane. If it is your macrocycle, it will dissolve in dichloromethane, okay. But the complex that is precipitated there, that precipitate, if you try to dissolve it in dichloromethane, the solubility got so much, I mean it can dissolve too much of fullerene inside. Fullerene alone is not soluble in dichloromethane or chloroform or whatever solvents, but if this precipitate is dissolved in dichloromethane, you can increase the solubility, okay, and you are also seeing the fullerenes band in the UV visible absorption spectrum, indicating that macrocycle is there intact, because you are also seeing the peak corresponding to the macrocycle here, okay. Macrocycle is there, fullerene is also there, and solubility of the fullerene is enhanced when you are encapsulating it with the macrocycle. That was the conclusion. And as I said, this has a blue emission, okay. The solution looks like this, bright blue. And if you mix it with fullerene, you see the emission is slowly quenching, correct? And completely the blue color, the blue emission is lost. These compounds are emissive in solid state also. So we take this macrocycle, grind it with C60, because anyway it is in solid state also rigid, it has a crown conformation. So if you mix it with fullerene, grind it, instead of heating it in solution, just grind it. Then also it should be able to, you should be able to push it into the void, right? So that was the idea. We did that and start off with, this is dark brown color and this, or maybe purple color in solid, and this is a white color macrocycle. Grind them together, you ultimately end up in getting a pale brown solid. This color was very similar to the solution that you got by reflex, okay. So you can monitor the emission. Emission also confirms by heating you can complex, by grinding you can complex the macrocycle with fullerene. So some demonstrations have been done, and now because you have a complex, you are sure by the UV visible and emission and NMR and mass and so on. When you record the NMR spectrum, you start to see the signal slowly shift, okay, which was not happening before, right. When you did the titration in solution, the signals were not shifting, they were just aligned one on the above. But if you grind it or maybe reflex it, the solids have a nice shift from that of the unbound macrocycle, free macrocycle, indicating that again this macrocycle has captured fullerene, okay. So these were the examples, and 13C NMR was also recorded. As you are seeing here, these signals are corresponding to that of the 13C NMR, right. Carbons of fullerene should also give you a signal. When it's a free fullerene versus the complexed fullerene, you must be able to see the shift, right, and that is clearly noticed by the signal deviations that you are seeing in the carbon NMR. So you can use all these techniques to extract information. That is the beauty of spectroscopy, right. So be thorough with your spectroscopy. 2-dimensional are you studying or not? So 2-dimensional is also useful. So that is in the advanced level if you want to establish the connectivity and through space interactions, through bond interactions, all that could be identified by 2-dimensional spectroscopy. Here this is a simple 1-dimensional spectroscopy we could conclude. This is a mass spectrum, right. It is a simulated mass is compared with the experimental mass, and both of calculated mass, if you do it with the compared with an experimental mass, they both are matching like a fingerprint, right. So indicating that again fullerene is complex. So we have done this, and if you take a conformationally flexible macrocycle, conformationally rigid versus conformationally flexible. Conformationally flexible example that we took was isobutyl one, okay. So this isobutyl macrocycle, if you take the same experiments we tried, we took this macrocycle, dissolved in toluene, also add fullerene, dissolve it, reflex it, but we didn't see any precipitate like what we saw in the previous case. That means flexible macrocycles are not capturing fullerene because they are very rapid movement, doesn't have a defined void to capture fullerenes, okay. So again, though emission shift is there, emission intensity has come down, again it indicates a dynamic interaction, not through the cavity but peripherally they bombard each other, right, and then they depart. 13C also shows that there is no shift, indicating it is not complex, okay. So what we thought was you have a rigid macrocycle, you also have a flexible macrocycle. Let us say you take both of them together and add fullerene. Will the fullerene go to rigid or it will choose a flexible, right? As you said, it actually complexed with the rigid macrocycle and not with the flexible one. So conformationally specific binding you could demonstrate, okay. Only the crown can capture fullerene and not the flexible one. So it is a conformationally specific binding. So when you control the dimensions, okay, by some means using simple organic chemistry techniques, you must be able to tell the macrocycle do a certain work. Here the work is capturing fullerenes, okay. Similarly now I think Prabhu is exploring for nitroaromatic encapsulation, detecting explosive nitroaromatics. So all that could be studied with such kind of fluorescent macrocycles. Here the variation is that the fluorescence response is going to give you a signal because it is already emissive, so it gives bright light. Any changes in emission intensity you will be able to detect it. That is the advantage with these macrocycles, okay. So I think that these are some pictures that we made for the publication. Similarly, various other reports are there in the literature, replacing coumarins with anthrazines. Anthrazines are also excellent fluorophores, okay. Macrocycles are built with anthrazines. Macrocycles are built with pyrenes, for example, polycyclic aromatic hydrocarbons. These are excellent luminescent compounds and they are quite stable as well. Tetraphenyl ethylenes, okay. This is also an excellent fluorophore. If you arrest the phenyl's rotation somehow, these molecules would be solid state luminescent. Because when you excite a molecule from the ground state to the excited state, right, fluorescence is happening from the excited state, from the singlet excited state. If the molecule wants to come back to the ground state, it has to release its energy, right? It releases its energy how? In the form of light or in the form of heat. Heat anyway you cannot see, but you want to get the light back from the molecule, whatever you have given it to it, right? But how it is losing? Losing in the form of light. So how it is happening? Some energy is lost, so the energy is coming out in the form of light, correct? But how it is losing energy? What are the ways by which a molecule can lose energy? Relaxation. How it relaxes? Bond vibrations, rotations, right? All this is what they do. They won't keep quiet, right? So they do something or the other. So stretching of bonds, bending of bonds, this is one way of dissipating energy. Another way is rotation, carbon-carbon bond, CH can rotate. All that is happening in the molecule. So if you can log this phenyls, let's say arrest this phenyl rotations, then people have shown that these tetraphenylethylenes can be a strong luminescent molecule. How? One of the ways by which you can arrest these motions are, you make a solid. In solids, rotations are restricted. I wouldn't say rotations are not there. Rotations are there, but it is restricted, right? So when you make these rotations restricted, the molecule has no other way to release light in the form of, release energy only in the form of light. It can only release energy in the form of light. Correct, no? So there is no other way, that unnoticed way or non-radiative pathway will be arrested. Only radiative path will become dominant. So radiative path is the light pathway which you are able to see, right? So this is an excellent molecule. You should read about, you should read the works of Professor Ben Zong Tang. Okay, he has published more than 2000 papers with only these molecules. So many papers have come. How to arrest, what are the designs, how you can play with these arene rings, how to tune the emission, all that he has published based on only this tetraphenyl ethylenes. Okay. So similar systems are this one, where you have sulfur and nitrogen, phenothiazines, and you also have acridins, you also have fluorines. Fluorines are one of the excellent emissive molecules. They also have very appropriate triplet energy states. You can harvest phosphorescence, not even fluorescence, you can even think of phosphorescence emission from such kind of molecules. Carbazole is another molecule which is adjacent to it. Both the singlet state, singlet excited state, and the triplet excited states are accessible for these molecules. So you can bring in fluorescence emission, you can also promote phosphorescence emission for these molecules. With all these molecules, they have constructed macrocycle, means you can think about the application possibility, right? Anything with respect to sensing, anything in the biological environment as is shown there, molecular recognition, right? For all of this, using as functional materials, for example, emission is there, so you can use it in devices which can give out light, put in electricity, generate light, right? Electroluminescence, instead of photoluminescence, you can generate electroluminescence. This is possible. So all this is put into the macrocycle now, and the spectrum is so broad. Scope is very broad. So if you want to read more about these fluorescent molecules alone, you can read this particular paper, right? Magnetic Chemistry 2025, which summarizes whole of a set of fluorescent molecules until now that is known in the literature, and what are their applications, right? How this field is now developing into, it even gets into material science. One of the applications that I shared in the very beginning was in column chromatography, right? Those old macrocycles. Now these macrocycles are slowly getting into material science, where energy storage devices are of focus, okay, for battery applications, right? Inorganic materials are sometimes, decomposing, they don't give long life and so on. So people are looking for alternatives. So organic based materials also people are looking for, because now more consciousness have come in terms of environmental friendliness, right? So in that case, organic candidates are the best, right? So people are looking for alternative sources wherein you can use these molecules for material science related applications. One of the focus area is energy. Okay. So organic flow batteries are one of the things that is coming up. So there also you will see some of such macrocycles, quinone based macrocycles are used, and people put it in battery, many reversibility it can show, lifetime is increased. So all that applications you can think of. Okay. So I think with this conclusion I stop. I think already I have taken a little more time. Prabhu is waiting. You also have sessions after this. Thank you.